Semester. This is a very special day because our colleagues at Intelligent Automation Incorporated here in the state of Maryland, they have generously sponsored our ISR colloquia that we are very grateful to them. And the president of IAI, Dr. Vikram Mani Honda, I hope I pronounced your last name right. Vikram is one of our very devoted ISR alumnus. In fact, he graduated under Professor Krishna Prasad in 1997, he was telling me. And he's now the president of this company. As you see, the folder in each chair sort of describes some of the capabilities of the IAI. I'm especially emphasizing this to our students because IAI hired 8 of our graduate students from this institute, I believe, and more than that, and also provided internships and many great opportunities, and in fact, the research activity still is ongoing and expanding in ISR in collaboration with our faculty members. I want to invite Vikram to just say a few words about IAI and their activities, and then I'll introduce our wonderful speaker. So please.
Thank you, Reza, for that kind introduction. First, I want to say it's a pleasure, privilege, and an honor to be able to support this. Many of you faculty know, but many of the students don't know, we have a long history with ISR. The founders of our company, Dr. Jackie Haynes and Lenny Haynes, are actually both graduates of the University of Maryland, one of them in ECE. I'm a graduate, Professor Krishna Prasad in '97. 2 of our senior management team, Ben Backrack and Children Lynn, are graduates of Professor Levine. We have Jason Wee, who's a graduate of John Barris. We have Baba Kazimi, who's also a graduate of Krishna. So it gives me and everybody else in the management team a lot of happiness that in some small way we can give back to ISR. So thanks, Jeff, for giving us this opportunity. There's enough material for you to read about IAI, but briefly, we're a small company, 125 people. In many ways, like ISR, about 60% of our staff have advanced degrees, PhDs. We work across the areas of robotics, communications, controls, and AI. And basically a research organization that works across these areas, doing research, productizing the research, and that's it. So without much ado, I think Rachel, thank you.
Thank you very much, and I hope we will see more of you here for this wonderful seminar series that we have. ISR Colloquia is arranged to highlight and feature the great research that's been done here in ISR. So once a month, we ask one of our faculty members to give a high-level sort of presentation on what he or she is doing. And today, I'm privileged to introduce one of my very good colleagues, Professor S.K. Gupta. He is a very known figure, not only in ISR, but at the campus at large. S.K. got his bachelor degrees at IIT Roorkee, and then master's again at IIT in Delhi, and then he joined our great institute here and finished his PhD under Professor Deinanu, who's sitting over there. And so SK was actually one of our first graduate students here in the institute. And then he moved on and went to Carnegie Mellon and worked there as a postdoctoral and research scientist. And then we were lucky to recruit him to come back, and he's been on our faculty ever since. One great thing, SK has done many, many great things, and if you look at his CV, he has over 5 best papers only, many prestigious awards. But one important thing that I had the privilege to work with him was the establishment of the new Maryland Robotics Center. And this is one of probably the exciting activities here in the college and in the institute. And today, he's going to give us an overview about the Robotics Center, but more so with an emphasis on his own research and where he's going in his lab. So with no further ado, yes.
All right, so what I'm going to mostly focus would be on computational synthesis today and using examples in robotics. So that's what the theme is going to be for today's presentation. So let's begin with systems perspective. So if you think about a system, most simplistic definition of system that you can think about would be a collection of components which interact. It's a very simplistic definition of system, something which have lots of parts and they interact. When you think about designing systems, there are two perspectives that you can think about, and both perspectives are equally important and you want to take both. One perspective is basically decomposition. So meaning that you have something very complex that you're being told to design, you start decomposing into simpler and simpler elements and define connections. Other perspective is synthesis. So you basically have certain building blocks and you try connecting them together and basically try to build something complex out of it. So the perspective that you may want to take, whether it is synthesis perspective or decomposition perspective, kind of depends upon the nature of the problem. So remember, I said system can be viewed as a collection of interacting components. So what happens in the system, that behavior of a system gets inherited both by the component behavior and the behaviors of the interactions. Right? So if you believe that the way you want to think about the problem is that you want system to exhibit a lot of component behavior, decomposition is a good way to think about the problem. Basically, you need a power supply, okay, you're going to find a power unit which is going to give you that, and so on and so forth. If, on the other hand, you believe that components are relatively dumb and you are going to get the behavior of your system mostly by their interaction, then synthesis view is a better way to think about it. And ultimately, you're going to need both. So we are not saying that one is better over the other. You will need both, but I'm just kind of giving you a very simplistic view of the world, basically. Right? So think about it this way. If you have a serial manipulator, now this is for the roboticists in the audience, right? If you have a serial manipulator, you know the degrees of freedom depend upon how many motors you have, kind of motion that you're going to get depends upon what kind of actuator you have. So largely, behavior of a serial manipulator gets defined by what components you have. So decomposition is a good way to think about it. You want a 6 degree of freedom serial manipulator, you need 6 motors. You want a revolute joint, you need a revolute. On the other hand, if you're trying to build a robot, which is a parallel manipulator, that's no longer true. Having n revolute joint doesn't give you n degrees of freedom. So what happens is that your behavior of a parallel manipulator actually depends upon interaction between these links. That becomes a dominating thing which kind of defines how systems will behave. So that becomes a synthesis view. So you want to now think about kinematic synthesis. So that's kind of perspective. So today's presentation, we'll mostly take synthesis perspective. So I'm not going to talk about, I've worked in both the decomposition and synthesis. Today I'm going to exclusively focus on synthesis. So my interest nowadays happen to be in basically simulation-based computational synthesis. In a minute I'll define what all these things mean. And I sample problems from 3 application areas: computer-aided design or design automation, manufacturing automation, and robotics. So these are the application areas which feed me the problems which I'm interested in, then using simulation-based computational synthesis to go ahead and work on. But my approach to research is the following. So, there are 2 different types of approach that you can adopt in your research. You can build a great theoretical technique and then go find applications where you can apply it. Or alternatively, you can investigate an application, find out what the nuances are, distill out some general principle, and then work towards building theory. So that's how I mostly work. So I get excited about problems which are challenging in nature, work on them, get something from them, and then can make contribution to more fundamental things. So that's kind of I work, and I'm really interested in building actually system and demonstrating that how ideas can work. So that's the in general approach that I take to the research. So what's a synthesis? Synthesis is basically starting with some very simple building blocks and building some complex structures out of them. It's a different from optimization problem because you don't know the complexity of your final solution, you don't even know the form of it. And behavior that's going to be exhibited by this final solution actually depends on both the component and the interaction. So think about it this way. So synthesis is a problem where you have a big collection of structural elements, you shake them, and out comes isotop. So what is synthesis? So in a way, synthesis, the way I like to define it, synthesis turns ordinary into extraordinary. So you have mundane building blocks that nobody cares about it, but you organize them in certain ways and you get isotop. Same thing, you get these mundane atoms, you arrange them in certain pattern and you get this miracle drug or a poison. So basically, synthesis is a process which turns pretty ordinary things into extraordinary things. So that's what the definition of synthesis is. Now next question is, so what can computers do in synthesis? Traditional view is that somebody with a great insight, a lot of creativity comes in, and those are the people who work on synthesis. And they create these wonderful things from very simple ingredients. Right? They make wonderful cake. All the field that you sample, that's what the view is. That a genius comes in and turns these very ordinary, mundane things into extraordinary. But what is happening nowadays is computers have gone very, very powerful, and they are beginning to play bigger and bigger role in synthesis. So, now using computers, you can search billions of combinations. You can actually create a structure which can have unprecedented complexity. Actually, some of the modern things which are being done, actually we cannot even imagine doing them without computers. And of course, you can use computers for productive collaboration between the computing technologies and humans. So this view graph shows you two examples. One is where an antenna structure completely synthesized by the computer, which has a lot of nice properties. Another example shows you an amplifier, which is completely synthesized by the computer. So computer-aided synthesis tools essentially amplify humans' creativity. So whatever creativity you have, if you're using the right kind of computer-aided synthesis tool, it can amplify your creativity. It allows you to do a lot more than what you can without such tools. So first observation is that computer-aided synthesis tools can actually significantly improve design solutions. Now, to go ahead and show you that this observation holds, I'm going to show you 4 examples from my own personal research. So the first example is that we are interested in I'll go through this example in a little bit more detail in the later part of the talk, so I'm not going to spend too much time here. So the idea is that you have a robotic boat that needs to block another intruder boat which is coming. This needs to be done in real time. So you basically, the two boats are fighting. So you need to come up with action selection policy so this boat can very effectively fight this other boat. Usually you code such policies in a decision tree, in a large decision tree. So what are the building blocks? The building blocks are simple commands. Go straight, make a left turn, make a right turn, increase speed, basically the boat control that you have. Decision tree basically says, if enemy is doing this, then you do this. So that's a complex decision tree that you're trying to build. So it's a synthesis problem. You start with basically these building blocks and generate this decision tree which can actually fight this attacking boat. So this work is funded by Office of Naval Research. Many people have contributed to that, this work. Peter and Atul and Max are sitting in the audience, I believe. So I'll talk about this example a little bit later in more detail. Second example is, So I'm going to sample lots of examples of synthesis examples. Second example is if you're interested in creating a drive mechanism for a flapping wing microwave vehicle. So the idea is to create a drive mechanism which is as low weight as possible. Building blocks in this case are your geometric features which can give the shape to the link, and ultimate structure is this mechanism which basically can take the rotary motion and generate a flapping motion. Right? And in this case, the idea is that you want to respect a lot of constraints, which are all kinematic constraints, and as well as be able to withstand the force and so on and so forth. So using synthesis technique, we have managed to create a flapping wing flying platform, and the weight of that platform is 38 grams, and it can actually take 33 grams of payload. And the reason why we are able to do that is basically that we are able to actually optimize the mechanism completely, and we use advanced manufacturing processes for using it and so on and so forth. So now this is the time for a little entertainment. I can show you quickly the video of that bird. If it plays. I'll just basically bring it outside and kind of play, right? So there's a tiny mechanism weighing a couple of grams which goes in the front. So that's what, basically most of the research is on that. So that just shows you this bird.
This is presumably not a windy day.
Pardon? This is not good. We have a version on my website which is what happens to this bird on a 15-mile-per-hour wind rate. So you can go check that video, and will give you some idea what happens. Oh, this is another little video. If it plays, you will see that. This was just entertainment, nothing more. All right. So, getting back to the more serious part of the presentation. Third example is that, so a typical challenge has been in 3D shape measurement community. So people came up with this great idea. Use this projector and a camera and project a light pattern on an object, and then use the camera to basically see what the distortion on and infer the 3D shape. People were stuck for a while because they would project a fixed pattern onto the thing, and they'll find out that either you can get good accuracy or you can get a good coverage. You cannot get both. Meaning that if you make your fringe width very, very small, you get good accuracy, but large areas, simply you don't get any discrimination and hence you can't cover it. What we started playing with the idea of basically adapted pattern. So you start with a basic fringe and then you apply, so in this case the building blocks are geometric distortions. So what you do is that you apply geometric distortions. So basically imagine a fringe pattern and you start applying different geometric distortion to it, right? And the idea behind this being that apply this geometric distortions and basically synthesize a custom pattern which will be projected on the object that you're matching, and you basically match the pattern with the shape that you're trying to match. So first observation that you do with the standard fringe, throw it away and then customize it. Second round, you customize the projection pattern, throw it, and actually simultaneously you can do both. You can get very good accuracy and very good coverage. And for this work, we received one of the best paper awards. So that's another example where your primitives are geometric patterns and you apply them on the graph structure which can get applied to basically this pattern, and using which then you can actually do very good shape recognition. Fourth example is from optical tweezer domain. So in this case, the problem is that if you want to do any sort of planning, you want to be able to estimate the trapping probability. So there's a laser-based system where you're trying to get this tiny particle to move. And if you want to avoid the particle that you don't want to trap and trap the thing that you want to trap, you really need to find out what is the trap. And the reason this thing is probabilistic in nature, because of all this measurement inaccuracies as well as the Brownian motion. Now, you cannot do planning without knowing these probabilities. And you need to compute these probabilities super fast, because if you can't, planning will not happen. Now, if you basically run the physics-based simulation and basically run multiple runs and get the probability estimate, it takes 10 minutes for one probability. Not going to happen anything in the real time. So what we did, that we did months of calculations of these actually on multiple different computers and generated a lot of data. And then we built this gigantic meta model, which is basically a large decision tree whose nodes are RBF, radial basis functions, and an entire tree organized around it on a spatial tree. So what it does is that now it actually be able to estimate the trapping probability with a very high accuracy using this offline simulation data in a matter of microseconds, so which enables basically very fast planning. So in this case, once again, the building blocks are radial basis functions, and you organize them in this gigantic spatial tree over parameter space, and then you can do very fast trapping probabilities.
So is the gigantic simulation and the associated meta model conditioned on the specific physical circumstances such as the fluid type, environment, the geometry, etc.? So if you change that, you need to do that again.
Right. Actually, there are certain parameters that scale very well. For example, laser power seems to scale reasonably well. But then there are other things. So, if we change the numerical aperture, then we need to recompute the thing. But in a physical setup, typically people are not going to change the setup.
So this is for really enabling speedy performance of experiments by chemists and others who would like to pull beads.
Right, pull the beads or grip the cells and do all sorts of excitement. So these are just examples of what role synthesis plays in. I mean, sample the problem from wide variety of domains. And by the way, that the paper, we got another best paper award for that, the word work as well. So this just gives you sampling of different things. And I'm sorry to my students whose name I'm not acknowledging, but I'm kind of also trying to pay attention to time. But I have wonderful students who are sitting in the room who did all the work. Okay. So second observation is that, so I hopefully convince you that synthesis, if you can do it, it can actually get you things that you can't otherwise. Now the second problem is that, or observation is that, developing synthesis tool can be very time consuming. And the reason for it is simply that you got to make large number of decisions. So when you're trying to develop the synthesis tool, you need to make large number of decisions. Every application throws its own curveball at you, basically, in terms of what the nuances might be. And often people would say, if you're doing any kind of synthesis, the solutions that you are proposing have to be human competitive. Otherwise, why would I be interested in using a synthesis tool? And second, solutions have to be human auditable. Because if I, as a human being, cannot audit your solution, some magic comes out of it and I don't understand it, I don't want to use it. Because it's going to be a problem. I mean, who knows what problem is brewing here, right? And utility of automatic synthesis tool gets greatly diminished if it takes you forever to develop those things. Okay? So now, basically a new field has been emerging for the last 10, 12 years, which is called computational synthesis. And the idea behind this field being that it will provide the foundations, the principle, how you would go and build your own synthesis tools. So the field just is defined, it's a mathematical and algorithmic foundation for doing synthesis. And the kind of things that people are interested in studying in this field is what representations to use, what algorithm approaches to use, what is the computational complexity of certain synthesis problems, and so on and so forth. So that's what these folks in the field of computational synthesis study. And computational synthesis is a highly interdisciplinary field. People from biology, people from chemistry, people from material science, mathematicians, logicians. Because of diversity of application, a lot of people are basically in this area. So this basically aims to provide principles for designing automated and computer-aided synthesis tools. So let's talk a little bit about what kind of thing that you want to synthesize. So when you want to synthesize things, you want to use a representation which is modular in nature. So you can basically go ahead and create a module and reuse it. You want regularity so that you can express it using very, very compact length, and you don't have to. So if you can exploit symmetry, repetition, or repetition with a minor variation, you want to use all of those things. And hierarchy, if you can actually build things in a hierarchical manner, that you want to do. So in general, the consensus seems to be in the synthesis community that structure graphs are a good way to think about representing your problems. You can encode lots of things using these structures. You can directly represent any mechanical part. If you give me any mechanical part, I can describe it using graphs. So I would basically, nodes would be feature types and their dimension, and their relationships are going to be positioned with respect to each other. Right? So I encode any mechanical part that you give it to me using the structure graph. You give me any mechanical assembly, I can encode it using the structure graph. You can actually, so if you have any kind of flow type of problem, I can model it using graph. If you have any sorts of action selection type of policy, you can model it. In that case, we will use probably decision tree or perhaps state transition diagram. So the point being that you can model a wide variety of problems using this system structure graph, which capture what your building blocks are and what are the interactions. And you can actually embed in these graphs complex formulas inside the node. You can actually embed another tree or another graph inside the node. And you can actually put similar kind of complex things on the interactions. Now, synthesis area, so automated synthesis area has received a lot of attention, lots of exciting things have taken place. People started evolutionary computing, where genetic programming, not genetic algorithms, but genetic programming became a big thing, where people wanted to automatically synthesize programs which can do useful things. A lot of stuff in reinforcement learning, where people wanted to learn how things are being done and learn policies from that. People have been looking into combining evolutionary learning and reinforcement learning. People have been building all kinds of cellular systems where you can learn the rules and then apply it, and that can give you complexity. So lots of exciting things are happening. So what is happening in the community is that basically there are a class of problems which are very easy to evaluate. And in that, people who work in that kind of problems are typically not worried too much about, reducing the number of solutions that they're exploring. Because you can evaluate fast, why not? Just go ahead and evaluate everything. Any reasoning would actually waste more cycles than trying to not reason about it, right? On the other hand, there are lots of such systems where actually, unfortunately, there's a tight coupling between hardware and software to the continuous nature, and hence, you're stuck with doing very complex evaluation. So that happens, then you have to start seriously looking at simulation as basically your evaluation tool. So now what happens is that you bring in automated synthesis people and you bring in this high fidelity simulation, right? So these are two different communities. When they come, so one natural thing would be connect the two together, right? But then that's where the collision happens, right? Why? Because high fidelity simulation people only care about the precision of their simulation. People take great pride in saying that I can do this simulation, and my accuracy is going to be 0.5% or 0.25%. They forget to tell you it takes 48 hours to compute that, right? It's not going to be helpful if you're interested in evaluating a million things. Synthesis people don't need that level of accuracy. They want to be able to discriminate between the two solutions. Which one is better? I don't care what your absolute accuracy. Just tell me, is this better than that? So what tends to happen in that case is that you cannot simply take automated synthesis tools and connect them with the basically simulation. So that doesn't happen. So that poses interesting challenges. And I'm talking about physics-based simulation, by the way. Whenever I'm talking about simulation, I would actually, in this presentation, would mean physics-based simulation, where physics somehow makes the things complicated and hence slow. So what happens, the fourth observation is that integration of physics-based simulation with automated synthesis presents basically new challenges. So that's what happens. And that's what basically I'm interested in. So what do you do? I mean, if you are going to be doing synthesis with physics-based simulators, you got to make lots of adjustment on the simulation side. So three tools which we contribute a lot to them. One is automated model simplification. So you give me something complicated, I'll try to see if I can simplify it. And I'll show you examples of all of these in a few minutes. And run it much, much faster. So it turns out that Given a problem, if you do right kind of simplification without compromising accuracy too much, you can actually get a couple of orders of magnitude, sometimes speed-ups. Automated model reduction. So sometimes it turns out that there are terms in your simulation equation that you can drop in certain range, in certain domain, and it's not gonna affect your synthesis performance. And automated meta-model synthesis. So sometimes first two tricks will still not create something which will be useful for synthesis, so you got to do automated meta-model synthesis, right? So these are the kinds of things that you need to do to simulation in order to make it connect with basically synthesis. Now, in terms of now synthesis aspect of it, see, if my evaluation was super fast, then I wouldn't care. I would just say, evaluate a billion things, who cares, right? But if your evaluation is slow and it causes problems, then there's the challenge. You got to make some improvement on the synthesis side too. So first problem is generation of sophisticated solution. How do you synthesize something which is sophisticated? I'll answer that question. And you want to absolutely squeeze out any unnecessary computation because evaluation is still going to be slow. And then you got to write representation because it matters a lot that what representation scheme you are using because your success depends on whether you're using the right graph. Is basically over a generative scheme, but what goes in there, what label goes in there, what details you include, what you not include. You use indirect graph, direct graph, hierarchical. I mean, all of those decisions play very important. And right kind of evaluation. So first deep point of the talk that I want to make is the following. Okay? So here we are, a couple of minutes on this one. So what happens in the synthesis community is the following. You basically write some kind of initialization program which generates a solution pool. This solution pool, you evaluate it, and then then you have some scheme which basically tells you what solutions have the highest improvement potential, and then you start with those and you basically start modifying solutions. And then set them back in the pool and you keep iterating, and then eventually, after a while, you find out if the thing is not improving, then you go ahead and select solution. Right? So now let's talk about what happens when structures are complex. So if structures are complex, what's going to happen is that you will be given such a graph and say, okay, this graph has the highest improvement potential. So now you can use genetic programming, whatever, you can use your favorite. But the question is, where to make the modification? It doesn't complicated thing where to make the modification. Genetic programming doesn't tell you where to make the modification. And what happens is that there are some fatal flaws. If they get introduced in a structure, the structure is not going to work. I mean, it's just destroyed and you can keep doing whatever you want to it and you're stuck. Now, what happens is that as your structure grows complex, both of these things come back and hit you very hard. It's very easy to do a one mutation and that comes back and it completely wrecks the solution. So now probability of you actually moving away from a complex structure and creating something which is useful actually drops dramatically. So what happens is that if you are interested in designing something which has 20 nodes in a decision tree, classical genetic programming is perfect. Fine, get you 20 nodes, 30 nodes, no problem. If you expect 1,000 nodes in your decision tree, classical genetic programming is not going anywhere after 35, 40 nodes. That's it. You are stuck. It's not telling you where to make a fix, and it will keep introducing little bug every time randomly in it and not doing it. So the two major things that we have to routinely do is the following. So modify solution basically, so you start with that, but then you identify regions to focus. Where is it that the change is likely to have the highest impact? And also, what are the fatal flaws and how do you isolate it so that you never send them back? So when you do your mutation, you never introduce fatal flaws. So instead of generating a complex graph, what you try to do is that you basically highlight with some probabilistic model that this is the area where you should try to do your modification. And also you generate these graphs to basically tell you what are the fatal flaw patterns, and please make sure that you change your mutation operator so that they don't introduce use that fatal flaw pattern, right? So that's how you kind of cope up with the complexity and make sure that now where everybody is stuck at 30, you can actually go to 1,000. Right? Those are the two tricks which allow you to basically synthesize things which are complex. Okay, so this is the computational framework that we use in our work. Basically, you similar sort of rehash of the previous figure. So you identify missing features, you synthesize features, integrate these features into solutions in operations. So that's very synthesis features. And then here you're using all the techniques at the bottom from the simulation to bridge the gap. So the 4 examples that I showed you basically use some variation of these techniques. Okay. So to summary up to this point, now I'm going to give you a little bit more specific details. Right? So what I talked about was the following. So there's a big community called Computational Synthesis, which I'm part of. A subset of it basically belongs to people who do simulation-based computational synthesis, because not everybody does simulation-based computational synthesis. So my interest is only in simulation-based computational synthesis. I don't work on other kind of computational synthesis problems. So these are the fundamental principles, and then computer-aided or automated synthesis tools basically get built for applications. And I'm interested in only those applications which involve structural and evaluation complexity. If the application doesn't have structural or evaluation complexity, I'm not interested. Right? So basically what we do is that we operate in these two spaces, and basically we learn something from here, we make contributions from here, add something here, and then hopefully that enables us to go after the application. So that's the kind of thing that my group is mostly nowadays focused on. Now I'm going to try to revisit the example 1 and try to convince you that using these tricks actually you can solve some interesting problems. So simulation-based computational synthesis can be actually used to solve some interesting problems. Now how much time do I have? 20 minutes? Okay. So basically, we'll talk about the work on automated synthesis of action selection policy for unmanned vehicles, which are operating in adverse environment with adversaries, which could be deceptive. And the work is funded by Office of Naval Research. People who work on this include doctorates, Steve Newport, Matt Schwartz, and Thakur. We collaborate with Energetics Technology Center, which is a non-profit organization situated in Southern California. So Bob, Steve and Max are from the Energetics Technology Center. Peter Schweck, Atul Thakur, and myself are from. Okay. So Navy has developed this new platform called USSV, Unmanned Sea Surface Vehicle, HTF. Their idea behind these things is that they'll be basically relatively important assets in the ocean, and you want to protect them. You really don't want somebody to come and collide with them and blow them up, right? This could be oil tankers, this could be oil rigs, some other important thing which is happening there. So they want to use these vehicles to patrol around the area and basically deal with if any situation were to be. Now, typical problem when you're dealing with this kind of situation is that, okay, so somebody says, here are a scenario and the kind of things that we are interested in regarding it. Typically, it will translate into some large action selection policy, and people would say, we'll code up a logic for this action selection policy, and we'll try it. The process of doing it extremely slow. So our hypothesis behind that would be that can you use simulation to automatically discover these action selection policies given the mission context, and then execute it, and then they see how well these things are doing. So that's the premise behind this. Basically, so scenario is the following. So here is an oil tanker, and here is your unmanned sea surface vehicle. There are a lot of friendly boats in the sea. Basically, so any boat enters in this which is not authorized, they are crossing the danger zone. There's a trouble. There's a buffer zone over here. So what happens is that if any boat which is not authorized, the moment they cross into the buffer zone, basically a USSV would have to go inquire, give the warning to the intruder, and basically tell it, get out of here now. So So if they don't, then you basically do something which Navy would never tell us what they do. They told us you block. So you basically go in front of them and you block. And you try to delay their arrival basically at the oil tanker as much as you can. Right? So the moment they turn, you just go in front of them. Because remember, they are not interested in blowing you. So they would try to avoid, sneak behind you and try to go do something. So your performance measure is basically how much can you delay. So if you didn't do active locking, how long it should have taken them to arrive at the tanker, and if you did active locking, how much you would have slowed. Right? Write the best possible code you can do. Make sure you respect all your fluid mechanics. You're operating in an ocean, so all of those things are relevant. So you cannot abstract this problem into non-physics stuff. Right? That's the problem. So the challenge in this case is that intruder might be driven by some intelligent person who may be actually taking all kind of deceptive actions. And this is stochastic space. I mean, you may have C states which may influence your ability to move, your turning radius, your acceleration, your velocity. All sorts of things can actually change. In state space, it's actually highly fractured, it's continuous. What appears to be a good action over here will be terrible action a little bit later in different part of the state. And then you want to find the balance between the safe and aggressive behavior. So it's a complex problem, required fairly complex, and by the way, it's a real-time policy. So you don't have a luxury of planning for 10 minutes and taking an action. You are operating in a very close proximity of this vehicle. You have to make a decision and act now. I mean, this is how these things actually work. So the way we went about solving this problem is that we developed a detailed USSB simulation model. And then we haven't yet gotten the USSB testing, so this block is still waiting. So you have a detailed USSB simulation model. Using that, you develop the USSB meta model. And then you use basically your meta model, and then you have developed a detailed virtual environment, virtual reality based setup, where you can drive these boats actually interactive. We'll talk about that. Then you can actually, even human can demo a policy. They were trying to protect this boat, how would they do it? So you can actually get programming by demonstration angle going into that. And then you can actually synthesize the policy, given a mission. And then you can compare the policy and try to see how that is. So that's the overall thing. So the first problem is that if you take, so our program manager in this case told us that use displacement physics. All you got to worry about right now is displacement physics. Don't worry about plane physics. Just work with the displacement physics. So what happens is that if you code up the 6 degree of freedom displacement physics on a simulator, I mean, these things are not drivable in any interactive mode because boats are very complicated, and if boats are complicated, you are solving a very complex problem over the mesh of the boat, and this boat is not going anywhere in the virtual world. You're stuck. So then you have to basically develop first all kind of simplification and model reduction to see if you can speed up this work. So you basically start with and doing analysis and trying to find out what are the wettable regions where I'll never be able to wet the boat and hence take it out from your geometry computation. Then you start exploiting spatial decomposition. Can you group certain clusters and create a large element on which you're going to do computation as opposed to very tiny cluster? Then you start exploiting all kind of temporal coherence. If on a particular little region on a boat, the force, the wave is not going to change dramatically, its force is not going to change, so you don't need to recompute it. So you exploit temporal coherence. And then of course you make the computation go in a parallel, right? So you code all of these tricks up by exploiting all of these things up. It turns out that if you start with a baseline, so baseline, let's say it takes you 0.8 seconds to compute one frame, right? With the simulation time step of 0.07 seconds. So you know that you are 10 times slower than the real-time performance, right? In this case. So if you do spatial decomposition, you speed it up to 0.18, you are still slower than the real-time. You do parallelization, you get 0.05, so you are now better than real-time. And if you do temporal coherence, you can do one frame calculation in 0.028 seconds. And of course, every step basically sacrifices the force accuracy a little bit. So roughly with about 6% error in the force estimation, you actually can actually do the computation, one frame computation in 0.03 seconds. So compared to the baseline, actually, which is the best known technique out there for computing these things, we can actually compute it faster by a factor of 28.5. So something that was taking 0.8 seconds to compute, now we can compute it in basically 0.2 seconds. So these speedups now allow us to set up a virtual reality system where you can actually go drive these boats around, right, in a virtual world, right? With the ocean playing around you, and you can get a feel for how the boat is. Okay. So using that, all the simulation, we have built a detailed virtual reality system. You can get a head-mounted display and drive this boat around, and you can see the virtual world. And actually, we are able to import basically ocean height field from one of the commercial ocean height field generator software. So you give us that you want Hawaii in the month of August, under what weather conditions we can import that wave and can run the simulation. So coming to the automated synthesis part of it, so the basic idea is the following. So you basically, so let's just talk about it, what happens. So what you use pure genetic programming. So in this case, if you use a pure genetic programming and synthesize the policy, if you use the best state-of-the-art available genetic programming and synthesize the policy, it turns out you gain little bit in terms of delay time, and then after that your performance doesn't improve. So pure genetic programming actually turns out doesn't do very well. So we have to start adopting our approach, which I just talked about. So you start with initially synthesized policy using genetic programming. So you start with that. You evaluate the policy in a large number of test runs. Then you try to find out where that policy is failing, what's causing the problem, right? And once you have found out where the policy is failing, then you start labeling what are the fatal flaws, or what are the critical problems in your policy where you were steering the boat the wrong way and somebody came behind you and actually reached the problem. So you try to figure it out, all such failure points. Once you have figured out failure points, then you try to find out what are the collection of states which actually represent these failures. And then you go back to genetic programming and basically synthesize a patch for that particular set of states. You put the patch back in your policy, you reiterate, you find another flaw, you do that, right? So what's happening is that you have evolutionary technique, which is genetic programming. Once again, contrast, it's not genetic algorithm, it's genetic programming. So you are synthesizing a decision tree, which can grow in length, and you find the fatal flaw. So now you are actually switching over to reasoning and data mining style of technique, where you're trying to basically understand what went wrong, and identify the state. So you're not trying to use reasoning to figure it out, I'm going to solve the problem. Just trying to find a state. And then basically say, I'm going to synthesize using evolutionary computing a patch for that particular problem. And then iterate. Right? So now you're interplaying basically in between reasoning and synthesis. I mean, reasoning and evolutionary techniques. Right? Go back and forth. So what's the meaning of it all? So I told you that you can actually successfully synthesize 30, 35 lines of code using genetic programming. So at any given time, you're synthesizing only 30, 35 lines of code. Then you bring a new state where things have failed, you find another 30 lines of code in that one, you plug it in, and then you find another state where things are failing. So at any given time, you're not trying to synthesize something very complex. You're only trying to synthesize a feature, a missing feature, and you put it in, right? So this technique then enables us to actually get the right level of complexification in the policy, and you can actually synthesize a pretty sophisticated policy. Basically, give you more details on it. So what happens is that you basically evaluate. So you start with a certain test scenario, you evaluate the policy, you find out the state of failure, where the actually failure happens. Then you go back in time and you try to find out where was the place where that failure, what was the point if we went past that, the failure is inevitable. It's going to happen. So you isolate those state of exceptions where you could have prevented possibilities, right? From that you find representative states, because you find lots of such states. And on that, because remember, you don't want to solve all the problems in one go. You want to keep the problem manageable so that GP style techniques will still have a shot at working. You find a representative state, and then you try to find the neighbors, which are the neighboring state in that, which still keeps the problem tractable. So then you find a tractable problem, and you go and solve it, and then repeat it again, right? Till you keep gaining enhancing performance. So now, how does this technique work, or how well it performs? So basically, we manually implemented a human competitive intruder. So we coded up a very clever intruder, and then we played that intruder against lots of people to just see that this intruder is good. Intruder is quite good. I mean, most people actually fall. Nobody can actually infinitely delay them. Right. So it's a very good intruder. It had deterministic behavior interprets with stochastic action. So it on purpose takes random actions to confuse you so that you can't find any patterns, right? Then we hand coded. So we said, let's hand code the best USSV policy that we can, meaning hand code means somebody sits down, writes a logic, codes it up, and then play it against this intruder and see what the baseline is, right? And then we say, we just use the same intruder and say, it automatically generate this USSV policy using the method that I just described. And then the question is, how well it's going to do, right? And remember, it's going to need a pretty complicated policy in order to cope up with that particular situation. So this just tells you that intruder can take all kind of random actions to confuse you. So here are the results. So what happens is the following. So you start, so this basically shows you every time so version 1 means genetic programming, version 2 means you did the reasoning, found a patch, rerun the genetic programming on that state, and so on. So AD means AD interplay between genetic programming and reasoning, right? So you found AD fixes in the code, and then you so what happens is that you initially try genetic programming. Yeah, so this is the baseline. So if you hand code basically a very good USSV defender, it can delay the arrival of the intruder at the board by 45 seconds, right? Initially, if you use pure genetic programming, first time around, it can do about 8-9 seconds. These are different, these are just showing you, average, mean, upper quartile, and so on. So every time you go basically find a state where things fail, you use synthesis process to find a patch for it and put it in there. So you can actually make sure that your performance keeps increasing. So which is a brand new result. I mean, other people have not managed to show it yet, that we are able to actually use genetic programming and reasoning in combination, and we are generating complex structure beyond what people thought that genetic programming can simply do for you. But that's interplay between, so we are not doing genetic programming, we're doing this interplay between data mining, reasoning, and basically genetic programming. So we are able to show that you can actually, so it turns out that we are able to show that you can actually beat the code written by humans. So the machine synthesized code can actually outperform the code written by humans, right? And we are interested in basically this trend line. So clearly, if a human spent more time, they could perhaps improve the performance, right? But these trends are what's more important to us than purely what the numbers are. So maintaining that slope is what's interesting. I can show you, honestly, the video was pretty details. So this is, in this case, the white camera. This is the USSV which is blocking it, and this is the intruder which is getting there. And once it zooms in, you can see a little bit more clearly that this is these things are operating in motion, evolving. And you have to respect physics in terms of braking and acceleration and all of those things. Actually, more interesting video, I'll just So this is basically machine synthesized behavior. Okay, so I guess my time is almost up.
Is there a kind of ring around the USSV that the USSV has to stay somewhere for intruders?
If we can, in this case we don't. In this case we haven't put that in. So it's allowed to come basically very close to it. But you can. So let me just finish one concluding slide, and after that I'm happy to take questions. Okay. I already said that. Of course, we have done synthesis in lots of other application areas. I'm not going to bore you with those. So in conclusion, you have system design, you can take synthesis view or decomposition view. You need both. Synthesis, then you have simulation-based computational synthesis people. A lot of people work on physics-based, simulation-based computational synthesis. That's the community that I belong to. And there are 4 major things that you need to do in order to solve these kinds of problems, which include meta-model synthesis, model simplification, bringing complexity into your solution, and learning from demonstration. So those are the 4 building blocks by which we can actually go and solve some challenging engineering problem utilizing computational. So with that, I'm going to conclude. And this is a bunch of other applications where these ideas are applicable. I'm going to bore you with those.
Let's thank our speakers. We have time for a couple of questions.
Yeah, go ahead.
I have a slightly irreverent question. So you published presumably how to design automated blocking policy synthesis. So what if I learn from that and I develop automated attacking policy synthesis?
Yeah, we do that ourselves.
So who would win?
So what happens is that this entire technique is called co-evolution, right? So what we try to do is that we use our own, blocking policy generator guy, and we ourselves try to synthesize the intruder, which basically does reasonably well. So you go, basically alternative, right? So you synthesize a good intruder, you synthesize a good blocker, and you synthesize another good intruder, and then you synthesize it. So it's an arms race. I mean, you keep escalating. And that's how all of these things actually work out. So you have to make sure that you can do both in-house yourself reasonably.
A simpler thing might be to send a really dumb attacker who is able to recognize which of the many boats in the area is acting like a blocker, blow that thing up, and then send another dumb attacker.
I mean, that's the problem that we are working on it right now. So next problem that we basically are working on right now is called N intruder, M defender problem. So the question is, if you're going to have given N intruder, M defenders, then what's your best strategy? So in that case, your strategy changes basically, right? Because in that case, your strategy of assuming that somebody won't hit and destroy you is no longer true. Because in that case, there are N attackers, so one of them can say, hey, I don't care, I'm going to just take you out. So we are now beginning to work on that. Yeah.
So when you look at the policy that's being synthesized by the computer, I mean, obviously a human can look at that.
Yeah.
I mean, what do humans learn by looking at the computer solution?
What humans
Yeah, I
learn
mean,
from
is
it?
there something about the policy that's automatically generated that a human can go, wow, if I thought a little bit more about this, I could have actually come up with this by myself? In other words, the horizontal line you showed could be moved up.
Yeah, absolutely. Absolutely. We haven't done that, but I'm sure that if human looks at it, not only look at the policy, if they just look at the behavior, they can say what's going on there, right? And they can code something better, right?
I mean, how much more compact is the human policy than the computer's generated policy?
Factor of 3 or so. Human policy probably factor of 3.
Smaller.
Compact.
Yeah.
Because humans, kind of, computer doesn't care if, there are 2 statements, they are kind of, I mean, coverage is the same and you can concatenate them in a single action, but computer is not worrying about that right now. Yeah.
So how sensitive are the solutions to the observation model? Because right now you're probably assuming that both the attacker and the blocking mode have access to exact positions. from
We put
some-
noise there, basically, right? So both of cases, there's noise there. So you know the position of your, other person with some noise, and we are assuming that both of them have the similar sorts of noise, basically.
But some of the real observation models will have singularities and
Sure.
things like that. For instance, you will not be able to tell very well if something is moving away or closer sometimes,
Yeah, absolutely.
especially if you use
Absolutely.
vision.
So
So
right
how
now, that
sensitive would
question
be
is
to that?
hard for me to answer without doing the experiments. But what I can say with a reasonable confidence that if we had that model incorporated in it, then we should be able to synthesize a policy, which should be able to account for that. Now, what we have learned right now, I'm not quite sure how well that's going to do, basically, right? But I'm reasonably confident that we can synthesize a policy. So the perspective being the following. I mean, currently, if you think about designing these things, if you're going to design an autonomous solution, right, the human codes it up, and the smart one, and thinks about it a lot, and goes ahead and puts it in there, basically, I mean, they will be able to figure it out a way to cope up with that thing. The code might be bigger and the longer, more complicated. They cope with it, right? The trick there, once again, is going to be that if you can find the states where things are not working out that well for you, and if you can do millions of simulations or hundreds of millions of simulations, then you will discover that what I was doing wasn't really making sense, and I'm going to put another patch which will take care of it. So I'm reasonably confident that we can generate a policy which should be able to cope up with whatever restrictions might be or imposed by the observation.
And are you using any receding horizon implementation of these policies?
These
What
are
kind
just
of
decision
look
trees
ahead?
right now.
They are decision trees, but they have to have some look ahead.
Purely reactive things right now. Just a purely reactive thing.
But they must have some dynamic model of the
Yeah,
modes
they do.
inside.
So, but very short term, basically, right? So you can estimate, basically when the boat will stop and what other acceleration might be, but that's about the extent of it. There's no serious planning going on. Which you could and then improve things actually dramatically. If you incorporated some planning component in it. Because there are all kind of complications that arise in the scene because once you start having islands and other boats, then people start doing deception at an entirely different level. They may hide behind something else, do a whole bunch of other things. But we are not doing these things right now.
Last question.
Good question. So, somewhat hidden from view here in the presentation for me was that two questions. You must be incorporating some sort of finite state assumptions about things like the ocean environment or other factors. And if not, you must have some sense of how the number of states grow. In other words, I'm thinking of some sort of a granularity, some coarse graining that is being done in order to say, instead of knowing exactly you're moving at this angle, at this rate,
Right.
you have this quadrant you move in, or some octave you move in, or something like that. I'm guessing this. Maybe I'm wrong. The other question really is because I can abstract out what a boat is at some level, rigid body in a flow environment, or a point particle or something, it is possible for me to think about the possible control loss and sensory motor in the sense of feedback loss that I might apply. And somehow those, with the purposes you have in mind, are to fulfill some strategies that you have in mind, to execute some strategies. So those kinds of theory-driven understandings seem to be not brought out when you go for this search techniques for developing your code. I mean, by search I mean these GP-based search